And the dean said, okay. And I said, can I have that in writing?
Yeah.
And I got it in writing. And then I went to the head of the pharmacology department, and I did the same thing. Will you count the biochemistry course and the physiology course and from medical school for your PhD in pharmacology? Yes. Can I have that in writing, please?
Great.
When I went to actually get my PhD, they called me into an office and said, Ann, it looks like you're getting your PhD in 1 year.
Welcome to Stimulating Brains.
Hello and welcome back to Stimulating Brains, episode number 23. It's my great honor to present this conversation I had with Ann Young, who is the Julian Dorn Distinguished Professor of Neurology at Massachusetts General Hospital in Boston. Professor Young had an amazing career with a lot of highlights that we all cover, including discovery of glutamate as a neurotransmitter, the Albin-Delong basal ganglia model. So in her part, the part that was discovered by Roger Albin herself and then her late husband, John Penney, and then multiple other things. We also talk about career building, advice, and so on, because Ann Young was the chief of neurology at Mass General Hospital, which is sometimes referred to as the best hospital in the world, or one of the best, definitely. Her aim was to build the best neurology service in the world when she was appointed chief there, and she certainly created a very exciting neurology service at MGH. She was also president of both the ANA and the SFN, which nobody else has so far mastered to do. So I'm pretty sure you liked the conversation we had, and it also directly builds upon the last episode we had with Mahlon DeLong, because, as mentioned, Ann Young also contributed massively to our understanding of the cortex basal ganglia circuit model. So have fun and thanks for tuning in. Stimulating Brains episode number 23. So Professor Young, it's such a great honor to be able to interview you. Thanks so much for taking part in this.
Sure.
I will have more formally introduced you by now, so we can directly start with the questions. So I always ask to break the ice, what do you do when not involved in science or medicine? I mean, you are retired, so you have probably more time now, but any hobbies or activities that you pursue?
Well, yeah, I live right on a lake up here in New Hampshire, and we have all sorts of wildlife. So I've rigged my yard with all sorts of motion activated cameras that record all the wildlife at night and during the day. And it's really fun.
Oh, that's amazing.
And then the lake is just delicious for swimming. So right around now is swimming for a few months, and that's really nice. And then we're up and I take walks every day with the dog. It's lovely. I read.
Great. Yep. Super. That sounds really cool. I'd love to see some footage of the wildlife cameras. That must be nice to explore. It's a great hobby. I can totally get that. So as a kid, speaking of animals, you, according to your Wikipedia page, based on your feisty nature, quote unquote, earned you the nickname of Tiger Annie. Do you want to tell us a bit about that? Like, how was life growing up for you?
Oh, yeah. Well, my mother wanted me to be a sweet little girl. I had a brother, an older brother, but I was unfortunately a tomboy. So she had to put up with me tearing around in t-shirts and jeans and getting dirty and exploring up in the woods. And so I had a neighborhood. I grew up in a neighborhood where there were a lot of little kids like me. And so there were several little boys, and I used to be terrors of the neighborhood. And that was fun. And and my dad was kind of impressed with my feistiness. I used to get in fights at school.
Okay.
So I would come home with sore knuckles and such. And my dad would, he's the one who called me Tiger Annie.
Okay.
And he would try to teach me how to fight better. But yeah.
Okay, so that's great. He supported that. Very nice. So we can get already some picture of you now. But let's speak about your professional career. That's of course what we are here to talk about. Who were mentors that clearly stuck out in your career, and also maybe turning points? What was important to get where you got?
Well, the most important person was Saul Snyder at Hopkins. He accepted me in his lab and really let me do kind of what I wanted. He always had something for you to work on, but he also, if you came to him with a problem and you had a series of experiments, he would often say, sure, go for it. And that was wonderful. And then when I got to the University of Michigan, the chair who recruited me, Sid Gilman, he was fantastic. He helped me with all my grants, helped me interact with the people down at NIH. He was very helpful. And then that was kind of about it. The rest I did on my own, I think.
Sounds great. So I mean, your research career has been filled with highlights. I think we'll just try to get through them if we have the time. And I think one of the key things is that your research provided some of the first evidence that glutamate was a neurotransmitter of, I think, in your study of cerebellar granule cells. But it also, I think, in general, provided first evidence or important evidence that glutamate was a neurotransmitter. Can you tell us more about maybe how it was back in the time? And
yeah, sure. Well, back in the time, acetylcholine, norepinephrine, serotonin, epinephrine, and for some people, GABA. They were all probable neurotransmitters, but acetylcholine for sure, and some of those others for sure. GABA, there was some yes and no. Eccles then sort of came in, and these set of physiologists, it was funny, back then, the physiologists tended to be the neurologists and or neurophysiologists. And the pharmacologists were the psychiatrists. And so it was interested, the psychiatrists couldn't care less what the granule cells used as a neurotransmitter, or for that matter, the corticospinal tract. So the first thing did with the cerebellar granule cells was that my husband was working in a lab that was using viruses to attack certain dividing cells.
Okay.
And he comes back to me and he says, there's this woman in our lab who can just take away all the granule cells and leave the other cells intact. And I said, whoa, what a perfect model to find out what the transmitter is. So I went to the woman who had been looking at this model, Mary Lou Ostergranit, and I said, can I get a litter of your hamsters without any granule cells for several weeks in a row? And she said, sure. And I could do these experiments. I think it took 3 different weekend experiments to show, one, there was no change in acetylcholine, serotonin, norepinephrine, none of that. Amino acids, the only ones that were changed were glutamate and aspartate. So in the next set of experiments, it turns out that glutamate and aspartate have been found to have both a high affinity uptake system and a low affinity uptake system. And it was the low affinity uptake system that was associated with just cellular metabolism. But many people thought, and in particular thought, well, glutamate, a high affinity uptake system, well, that could be a neurotransmitter in activation. So we looked that weekend at aspartate and glutamate uptake, and it was the high affinity uptake that was changed. And then the next weekend, we got an amino acid analyzer to look at some samples. And yes, only glutamate levels were changed, not aspartate. So that was pretty good evidence. And nobody did much else about that. When we got to the University of Michigan several years later, we started working on the corticospinal tract.
Yeah.
And that ended up likely being glutamate as well. So yeah, that was pretty cool.
Very, very cool. So it is even, it's so fundamental now that it makes it hard for us younger people to even imagine a world without this particular knowledge that glutamate is a neurotransmitter. It's so, it's obvious, we learn it, obviously it's cool, and even in high school probably. So why, I think establishing glutamate as a neurotransmitter was the slow process, according to the internet, over a period of 20 years, dating back from the 50s. I think back then somebody injected glutamate into the ventricular system and showed that there were some cramps following. Is that
yeah,
true?
And they were also squirting it on cell bodies and seeing what kind of reaction. And it was a mix of reactions, some excitatory and some spreading depression. And again, when you looked at the physiology, it wasn't that helpful about defining a pathway.
Makes sense. Yeah.
And so, it went along slowly. And I wanted to be in that field because I figured it was going to be slow and I wouldn't have to look at a whole lot of competition. And then the next thing you know, boom, everybody and their brother is working on it. So
interesting. So you saw an uptake of this field taking off once you published these results. Is that okay? So why did it take so long? So I read that since glutamate is essentially everywhere in the body, maybe that's why nobody suspected it. Because as you mentioned before, so at least what I read, it was decades after the identification of acetylcholine, norepinephrine, and serotonin. Also, dopamine, I think, was known.
Yeah. Mm-hmm.
But you could argue glutamate is the most important one, maybe, right, or the most ubiquitous one. So why was that one discovered so late? Is that
all the amino acids were suspect because they had such an important role in general cellular metabolism, particularly glutamate. And it was the fact that you could look at brain concentrations and they were high compared to other organs, but were they huge? No, but they were high.
Okay.
And those levels changed when you lesioned areas that you thought were projecting to somewhere.
Okay.
And but there was a lot of skepticism. I mean, when I was at Hopkins, the head of physiology, Vernon Mountcastle, he didn't really even believe in transmitters. He really only believed in electrical transmission. And it was only sort of during the time period I was getting my PhD that he started to, well, okay, maybe there's some transmitters.
What time was that, roughly?
That was 1969 to 1973.
Yeah, okay. Yeah, Mountcastle, I think, is still very much known for the cortex and so on. So he did a lot of cool stuff there. But it's so interesting to hear that back in the day, he was not believing in neurotransmitters as well.
Yeah.
Very, very exciting. So it's always, it's so hard to, as a young person, to understand these things retrospectively. If you, read the literature, let's say, backward in time, it's very hard to understand that. And I feel only talking to people that lived at the time and did research at the time can really, embed us into this field and this feeling. So that's really, really amazing. So I guess the next and maybe even bigger, or I don't know if it's bigger, but another really big highlight of your career is, of course, the circuitry model of the basal ganglia and cortical thalamic-cortical interactions. And I think I told you in the last episode of the podcast, I interviewed Mahlon DeLong, and a key focus there was also the model of the basal ganglia. And I think now, brushing over history, is often referred to as the Albin-Delong model. And often, again, like two key papers are being cited, one from your team at Ann Arbor and one from Johns Hopkins, where DeLong worked at the time. So Ann Arbor, Michigan, that paper was authored by Roger Albin, and then yourself and your late husband, John Penney.
And everybody called him Jack.
Jack, okay, good to know. Good to know. So when I asked Mahlon what the contributions between the two teams had been, again, very hard to disentangle now from, looking back. He didn't say too much, but he mentioned that your laboratory had focused a bit more on the motor domains of the basal ganglia, while a key contribution of his team, also together with Alexander and then also Hage Bergman and so on, had been the parallel loops of the basal ganglia with motor, associative, and limbic domains. Mm-hmm. Is that fair to say? Do you have the same memory? What's your take on this?
Yes, actually, yes and no, what he says. Kemp and Powell also looked at some of these circuits through associative and limbic, others, cortices. We had, what happened with my husband, Jack, and I, was that when we came to the University of Michigan, we took over a movement disorders clinic. And we saw a lot of different kinds of movement disorders. And we had no formal training, like gone to Marsden or Fahn or somebody else. We had just obtained our experience, right, seeing the patients. And both of us were struck by how the descriptions in the literature were not really that descriptive of what the patients actually look like. Okay. So we made
an example.
Well, yes. If you ask Parkinson's patients to tap their fingers, they may start off slowly, but then it gets faster and faster and faster, almost faster than you can do it. And then you ask them to stop, and it takes a little while to stop. Well, that's odd, right?
Yeah.
So, and there were a bunch of other things that just didn't make sense with the old way of thinking that Parkinson's is slow and, Huntington's is fast and yada, yada, yada. Yeah. So we started saying, okay, what pathways have which transmitters? because if the cortical striatal pathway is glutamate, then what is the striatum doing? Itself. So we started to make these lesions to see what happened downstream. And in doing that, we had to measure in our hands receptor concentrations and affinities, because we had hypothesized that if you removed, say, a GABAergic input to a neuron, that it would become super sensitive and increase the number of GABA receptors, right?
Okay.
So this required looking at an anatomy and a drug effect or a drug binding. So we really, the two of us, invented the tritium-sensitive quantitative autoradiography that you could do with tritium-sensitive film.
Oh, interesting.
And so you could be very quantitative about it. And we were able to show that, one pathway had to hook with another, if this circuit was going to make any sense. But there were also experiments we did where the outcome was not what we predicted. And that, you asked about eureka moments, that's where we go like, what? And then we go, it has to be that there's both a direct and an indirect pathway. You can't just say the striatum does something to things and it's all the same. No, it's very different. And now Mahlon DeLong in his chat with you, he did mention the fact that we worked on rodents, and in fact we did, and that he worked on primates. Now, unfortunately, he may have worked on primates, but we worked on humans as well, on human brains, post-mortem human brains. And we really published everything that we had discovered in the rodent, in the human brain, with Roger Albin and Tony Reiner and a bunch of us. And that made a lot of sense of how the circuit could be put together and whether you would predict that Parkinson's disease would have an overactive subthalamic nucleus and you could lesion them there.
Interesting.
Or globus pallidus interna.
So to ask a few naive questions, so in humans, was it post-mortem? Then you measured concentrations of the, or you made lesions as well afterwards?
No
that's
lesions.
Not possible, right? Okay. and then in the rodents, like what was the general method? So you made lesions, but then you afterwards and before the lesion, you measured the concentration of the transmitters in the receiving part, or where you made the lesion, or both, or
both. Yeah, you could measure the receptor concentrations throughout the striatum and projection areas. You could get a nice cut through where you could hit all of them and get measurements that weren't just, one concentration, but you could do a whole dose response curve. Cool. You could do a whole inhibition curve, like are there better benzodiazepines for the external globus pallidus than for the internal globus pallidus? Yeah, there probably are. That kind of thing that we could do and say.
Who came up with the direct and indirect pathway terms? Do you remember?
It was actually a guy named Mackenzie. He was John Mackenzie, who worked before either Mahlon or I think. And I believe he's from the UK.
Okay.
And did work, and he coined it, but didn't coin it based on either of our stuff, you know.
I see. Okay. And were the dopamine receptors already known there at the time, so that you had D1 and D2 receptors, or was that also part of that?
Oh, that was a big part of it. So I was, when Jack and I first got to Michigan, there was a guy at Michigan State University named Steve Katai. And he had a group of physiologists, including, I don't know whether you know a guy named Charlie Wilson. Anyway, they're great physiologists. And they were taking the place apart with electrophysiology. And Jack and I went over to see them, and we're talking to them, and we're going like, hey, yeah, but the dopamine is inhibitory on the striatum. And they're going, no way. And we're going, well, I mean, if you look at, the pharmacology, the dopamine and acetylcholine are kind of at odds with each other, and that's perfect for inhibitory. No, they said. When we come in there and are recording from the striatum, dopamine is always excitatory.
Mm-hmm.
So now we're going like, how can that be? And I would say it took a year or so, talking with these guys back and forth. Yeah. Also, looking at the localization of D1 in substance P cells versus D2 in enkephalin cells. Those were all really important things to understand.
Absolutely. It's so funny that I think it's always harder to accept that it's both. If you say it's excitatory or inhibitory, that becomes the question, and you rarely think it's going to be both, right? But I can imagine how tough that is.
Yeah, but it was so perfect talking to this physiologist who said, no, it has two different effects. Mm-hmm. Or no, it has an excitatory effect. If it has an inhibitory one, we don't know what it is.
Okay.
And then it became clear.
Great. So together with your late husband, so Jack, you mentioned John Penney, you had started a laboratory at the University of Michigan, Ann Arbor, studying the anatomy and pharmacology of basal ganglia. So you already mentioned a bit that you started also clinical work together, and you right. Essentially led the movement disorders group. Was that the main motivation to even think about, hey, let's map the basal ganglia, let's create a model? Or did the model rather emerge with, bits and pieces of evidence that came in your experiments? Or was it like, when did the idea of creating a basal ganglia model emerge?
Oh, pretty much right from the beginning. I mean, okay. My husband was an anatomist, so he always was thinking the anatomy. And I was pretty good on the pharmacology. And my husband was photographic memory, and he could speed read. So I grew up dyslexic. So my husband, though, could read everything. By the time I was in medical school, we met very early, and I realized that he could read all the assignments and tell me. He could summarize really well.
Wow.
And okay. So, and that was true, when came home in the evening after we had put the kids to bed, then he would read papers and I would read abstracts that he told me to read.
Okay.
And that's how we did that.
That's very interesting. It also seemed like I read that somewhere, probably also on Wikipedia or on a different page that summarized your work, that you also divided, as you said, also then the clinical work. I think so your husband was more focusing on hypokinetic movement disorders, you more on hyperkinetic. So your disease essentially was Huntington's, his was Parkinson's a bit?
Yeah, mine were Huntington's and tic disorders.
Actually. Tic disorders, okay. Yeah. And then also, I think, as you mentioned, he did anatomy, and then I think he was also, computationally.
Oh yeah, very big. Yep.
Okay, yeah. And then yours was pharmacology. That it sounds so lovely that you apparently made a whole together. Whole. So you mentioned that you grew up dyslexic. How did that impact, maybe to briefly intervene, your career, or how did that work out? Because you were super successful, right? So it's maybe encouraging to talk about this for others.
Well, I was very lucky. I didn't get any help. I was in the time period when nobody cared if you were dyslexic. And the problem was I was so slow in reading that I couldn't finish tests or anything. And by the time I went to college, I couldn't take many of the courses because they required too much reading. So I did have some trouble getting past English, for instance, and that kind of thing. But in terms of reading science, everybody reads science kind of slowly. So I wasn't, proportionally that much slower reading science than the others.
That's a good point. Yeah.
But Jack changed the whole thing. So he could focus in and read this stuff and tell me.
Great, interesting. So maybe going back to the model, how much of it would you think is still true today? Probably tough questions, but
that's a tough question. But I think it is still providing sort of a scaffolding on which people hang their hypotheses. And there is so much new work that also deserves new hypotheses,
Yeah.
And I think that's coming out a lot with optogenetics and some of the other approaches, which are really, if we had them back in our time, it sure would have been exciting. But seeing it now is also wonderful.
Yeah.
And
super. Yeah, I totally agree. It's such a helpful construct that even if it helps just to motivate more complicated additions to the concept, it's still helpful. I think I totally agree. It's still taught today, the direct indirect pathway, and I think it's a good thing that it is. So it at least gives us a good and fairly simple understanding maybe of the basal ganglia, and then we can add on to it. So maybe speaking about the next disease. So Roger Albin, who was the first author on that main, or one of the key papers, now occupies a faculty position still in Michigan, which is named in your honor, the Ann B. Young Collegiate Professor of Neurology. And I Googled him from his profile. He seems to also study Huntington's disease. And that was a big topic for you as well. So 1981, you traveled with Nancy Wexler to Lake Maracaibo in Venezuela. Can you tell us? Maracaibo?
Yep.
Can you tell us something about that? Why did you go there?
Well, I would say that I went because I was seeing Huntington's patients in Michigan. I had inherited actually quite a large number of patients with Huntington's. And frankly, this was an opportunity of a lifetime to be able to go with a team to a remote country, try to examine all of them, sample all of them.
But why even go there? So apparently we have to tell the listeners there's a population of Huntington's.
Huge population. Well,
Yes.
let me.
That's
I'll back up.
key information. Okay, yeah.
Yeah, I'll back up because in 1972 was the 100-year anniversary of George Huntington writing about describing Huntington's for the first time. And at that meeting was a guy who showed a film of what appeared to be Huntington's disease down in Venezuela. Okay. And it was as if the entire town was part of Huntington's family. So in 1979, Nancy Wexler, they had been looking for a big family because the geneticists said recombinant techniques now allow us to map through the family if we have a big enough family. So that was David Hausman who came up with this. And so when Nancy saw the size of this family down in Venezuela, she arranges to go down, and I'm the lucky one who gets asked to go down as a neurologist. And there were 3 others of us, but I'm going down to be part of the group that goes down to the town on stilts down in a lagoon. Well, it was a pretty unbelievable experience. And I did it for 22 years in a row. And I must,
back and forth?
Going down to Venezuela just for maybe 3 weeks a year.
Yeah.
And then coming back. But during that time period, we got thousands of blood samples, skin samples, and sperm samples on people, and brain samples on people, and that's how the gene was isolated. So that was
very cool. Can you draw us a picture a bit of how that town worked? Like if so many people there are affected with the disease, do they have specific cultural things in place or?
Well, they live off the fish. They fish out of the lake.
Okay.
And they sell, if they can, some fish so they can buy some vegetables and other things. All very impoverished.
Okay.
Living in, when they lived in Maracaibo, they might have a cement house, but chances are it's tin and cardboard. And you get out to the outer towns, and there it's definitely tin, cardboard, a floor that's basically made of packed garbage. And everybody's living in one family, may be affected by multiple members with HD. And then the kids and unaffected members try to take care of them, but that's not easy.
Sure.
And it's just a very, very moving environment.
Yeah.
Tried to help them as best we could.
Sure.
I want to bring a therapy back to them.
That'd be great. Yeah. Good point. So it led to, as you mentioned, discovery of the gene. I read that Jim Guzella was the probably first author that discovered the location of the gene. And can you summarize, how that happened and how long it took and how that maybe emerged from your project?
It took 2 years. We started sending him samples in 1981. By 1983, he had the location of the gene, not the actual gene, but the location on the short arm of chromosome 4.
Yeah.
But it took 10 years for the final identification of the mutation as an expanded CAG repeat. And that then was the key thing.
Yeah, of course. Yeah, for also for their diagnostic tests and so on. But yeah, very, very interesting. Yeah, bringing back a cure. I wish that will happen soon. So you I think you continued Huntington's work, and you also founded then I think soon after that. So at least in 1991, you were appointed chief of neurology at MGH at Massachusetts General Hospital, and also the Julian Dorn Professor of Neurology at Harvard Medical School. And that is such a key achievement. Maybe for the international listeners that might not know MGH, it's rare, but this is probably the best, one of the best hospitals in the world. And the neurology service is really excellent there. And you were also the first female service chief in the hospital's 180-year history, and also the first female chief of neurology at a teaching hospital in the United States. So that is such a great honor. And can you tell us a bit, was there a secret to this, or was it, hard work, or what led to it?
No, I don't think there was a secret any more than I was a very outspoken person.
Yeah.
And so I guess, I kind of expected those things in a way. Going to MGH, that was one of the things that drew me to going to MGH, is if I could be the first woman head of a service. And I know they asked me what I wanted to do with the service, and I just told them, I want to make this the best neurology service in the world. And I meant it,
Yeah.
I tried my best. I don't know whether I succeeded, but did a fairly good job.
I'm sure you did. Yeah. Absolutely. Very nice. So that's so interesting that it seems like some genius people like you may have that. I once heard Bob Dylan say something similar, that he said he just as a kid he knew he was exceptional. And it's kind of tough to say it. Or you then wonder if what's the selection bias here, right? How many people think they are exceptional but are not? But apparently for the two of you, there must be some just inner feeling or knowledge that you'll succeed and get there. This is
I didn't doubt myself.
Yeah,
and there was a story. I don't know whether you find any stories, but when I got to medical school at Hopkins, I went to the dean because there wasn't any MD, PhD program designed yet. The dean said, you design it yourself. So I said, I'd like to take the first 2.5 required years of medical school courses. And then I want to take the last 1.5 elective courses as part of my PhD.
Okay.
And the dean said, okay. And I said, can I have that in writing?
Yeah.
And I got it in writing. And then I went to the head of the pharmacology department, and I did the same thing. Will you count the biochemistry course and the physiology course and from medical school for your PhD in pharmacology? Yes. Can I have that in writing, please?
Great.
When I went to actually get my PhD, they called me into an office and said, Ann, it looks like you're getting your PhD in 1 year. I was going to get the whole thing in 5 years. And they said, that's too fast. It looks like we're giving out cheap PhDs at Hopkins. Mm-hmm. And I said, well, I really don't think so. I did get quite a few publications out of it. You approved my thesis, and you put in writing that that's okay.
Yeah.
And they kind of looked at me, and I said, yes, I still have those letters in writing where you promised I could do this. And let me tell you, I said to them, if you refuse to give me the PhD, I will make sure that every student I hear of that is applying to Hopkins, they know that you guys aren't keeping your word.
Wow. That's
and then I walked out.
Yeah. And it worked. So you got it in record time.
Yeah.
That's amazing. Yeah. Very, very cool. Thanks for sharing that. So yeah, it's really so impressive how much you accomplished. We get to other things as well, but then at MGH you did, and now continuing the work on Huntington's disease, maybe with a cure later. You founded the MGH Institute for Neurodegenerative Diseases, so the MIND Institute, and apparently were given an entire building in the nearby Navy Yard. Is that close to the Martino Center here in Boston? Yeah. Okay.
Yeah.
So how was that like to create a building? I mean, it would be tough for me to create a smaller lab with a few rooms, but a building, that's a big thing, right?
Well, my husband and I were keen on trying to get a group of investigators together who would all complement each other and who were all good collaborators. And I knew this building was coming up for proposals because I was on a space committee, and I'm saying, so who's made a proposal? And at the time, the person said, nobody. Mm-hmm. So I said, you're getting a proposal. So I made up, in a week, I made up a proposal for using all the space, who the investigators would be, what their grant status is, how many square feet they should be covering, you name it, all the layout, and got my husband to put some spreadsheets together for me.
Yeah.
And then, this is the way we'd work. And then I put it together and submitted it. And big meeting I had to go to. He was out, it was right before he died. He was out in Aspen skiing with my daughter. I presented this, and they gave me the building. They said, this sounds like a really good use of that space. And I had done some space dealing, trades, and this and that and the other thing.
Yeah.
But
that's amazing.
It was really fun.
Is that still in use in the same function?
Oh, yeah.
The MIND?
Yeah.
Okay. Mm-hmm. Super. Very nice. You were also then speaking about more success. You were president of the SFN, the Society for Neuroscience, from 2003 to 2004, and then of the ANA, so the American Neurological Association, from 2003 to 2005, making you apparently the only person in history that had both titles in their CV. Again, the same question: what led to the success? Maybe it's the same answer, but any tips of how did you do that?
I don't know. I mean, I think somebody must have thought I'd be good at it.
Sure.
And so they voted me in. I mean, there were small committees, I think, that do it. I don't think it's not like you're voted in by some giant number.
Sure.
So.
And I mean, as chief of the MGH, that probably helps, right? To get there. Yeah. So maybe to wrap up already slowly with some rapid fire questions that are easier to answer. So speaking about success, do you have any tips or thoughts about females in neuroscience and medicine? So especially any advice to young researchers or clinicians? especially female, but maybe also young in general, people entering the field?
Yes, the thing is that you, and this is females particularly, but either male or female, you have to really think hard about what you're worth. And you should not feel shy at all about asking for what you're worth. But you should be able to show somebody why you're worth that much.
Yeah.
See what I mean? So you have to have like some kind of proposal or vision or return on investment. If you give me this much, I'll bring back this grant, that kind of thing. But you have to stick up for yourself. Most women don't say, I need a raise.
Yeah.
And that's not true. The guys all do, and everybody needs a raise.
That's the quote of the day, certainly. Yeah.
So, that's the main thing. I think, I do think you don't want to be, women are often said to be a bitch or something like that. And so you do have to be careful that you don't get to be called one, And that's sometimes with women who are trying to stick up maybe a little too much for themselves. You don't want to, try to say that you're the greatest thing on
Interesting
earth.
though. I mean, can you elaborate a bit more? Because I could, argue that probably if men stick up as much, they are not being called a bitch. So, often.
Right.
So, isn't that still unjust that, as a woman, if you maybe ask too much often in our culture, you would already seem more greedy than a male that would do the same. So isn't that part of the problem?
Well, I agree, except that there are some women who are just evil.
Okay.
And
there are male too, but yeah, okay.
Well, it was interesting when I was being interviewed to come to Mass General. The head of psychiatry asked, well, how do you deal with these, men, women, sexual harassment? And my answer was, well, really, when it comes right down to it, men can be jerks and women can be jerks.
Yeah.
And, you don't want either one of them around. You want people who are going to try to help you, put you in a better place. That's what you want.
Yeah, absolutely.
And not people who are trying to prove their value over yours and, all that kind of stuff. So.
Absolutely. So we briefly talked about the dyslexia, and were there other issues in your career that you struggled with, or other fallbacks or episodes where you thought this was a waste of my time, like negative things in the career of a scientist or clinician?
No, I mean, sometimes they asked you to be on too many committees and things like that. I think my biggest problem was I have a very bad temper. Okay. And after Jack died, I became extremely depressed and saw a psychiatrist who said that, based on my history, I'd been bipolar my whole life, and the temper was part of that. And thank God I had a husband who kind of tried to damp it down for me. Okay. And and I got good treatment, and that's really made a huge difference. So,
okay. Did the manic phases or the positive phases of it then help sometimes, like give you energy to write grants, or
there were times when I had incredible energy level for doing things. Just this building, for instance, the whatever, putting together the proposal and this and that and the other thing. Yeah, I would have those phases, but then I'd have a lot of bad depression.
Mm-hmm. All right. Maybe speaking about not anymore about failures, but about the opposite. I mentioned, or you mentioned, eureka moments before. So, and we have talked about some. But was there any other moment that we didn't cover yet, where you thought, "Wow, this now I understood it," or this is such a success, or things in your career, positive moments?
No, I well, I tell you, there was the huge enthusiasm that I think everybody in the Huntington's field felt when these new antisense oligonucleotides had come forward to be tested by Ionis and Roche together.
Yeah.
And that went into a clinical trial that everybody so hopeful for, because it reduced Huntington in the brain.
Yeah.
And then, out of the blue, the data monitoring committee stopped the study and stopped it, saying that the patients were getting worse than the placebo. And it was as if, well, for me, I felt like I had been stabbed in the heart. For me, it was like, this could be it. This could be one of the first actual effective therapies.
Yeah.
And, another company had a similar approach. It also had to be stopped. So now everybody's going like, holy cow, what do we do next?
Yeah.
But there are people working on it, thank goodness.
Sure, of course. Yeah. What do you think about maybe, this is a podcast about deep brain stimulation, and obviously your work is very instrumental for
Yes.
that as well. But what do you think about deep brain stimulation for Huntington's disease, maybe?
Well, I've referred people for it. It's hard to know how much better they were. I think in the beginning they were somewhat, but then I also think there was a certain amount of neglect of their of the side that was better.
Yeah. Okay.
There was also some seeming neglect. I don't know why, but I didn't do it on many more patients. Have you done any?
So just rarely done. We had one case, interestingly, with subthalamic DBS at Charity that did really well. So interestingly, and but it might be so. My specialty is to localize the electrodes precisely, and it might have been even that it was pallidothalamic tracts that were just traversing dorsal to the STN, and but that patient, I would say, and that was, I think, the only real case we had in Berlin, and I just started here in Boston, so I haven't had much experience here. But in that patient, I think it's fair to say that without the therapy, it was even life prolonging for him. So in that case, but it's an N=1, so I don't have much experience. Maybe a general question: how did your clinical activities nurture your scientific understanding, and vice versa?
Oh, it was, I just feel very strongly that MD, PhD, particularly when I split it the way I did, where, what I was doing in the laboratory directly reflected on what I would see in the clinic, and vice versa, and you could ask certain patients what their tasks were. It's always amazing to me that a Parkinson's patient could be slow and tremulous on one side, right? And totally dyskinetic on the other side.
Mm-hmm. Yeah.
And that was amazing to me. And then when you watch the whole sequence going between, bilateral Parkinsonism to then changes across the body, those things to me were just fascinating. And so
absolutely,
to look at those in the lab was also.
So it made you a better scientist and a better clinician, probably.
I hope so. Yeah, I do hope so.
So you would, and then maybe, so you would still say apparently that the clinician-scientist career is a viable one to pursue today. But do you also see that the density of actions in the clinic, or that the speed, maybe the pace, has become faster, and that it might become more, let's say, in both science and clinical practice, that it might become unsustainable or harder to sustain these days? Do you see that?
I do think so. Yeah. I think it's just horrible what medicine has become, with this high turnover and quick. In the last years of practicing at Mass General, I doubled the time I gave myself for every patient, because I just said, I'm in this to help the patient, and it's not going to help me any. And, but it's actually one of the things I do now instead of practicing is I fundraise for the department. And fundraising does allow for some people to get some support to make their clinic, make them not so dependent on every patient they see.
Yeah, that's great. So what do you think about the future of neurology? What concepts might emerge in 10 years or in 5 years? A cure for Huntington's?
Man. Well, no, I do really hope, and I think there's possibilities that we'll have a cure for Huntington's. Much better cure, I think, for Parkinson's. And who knows? I mean, so far the Alzheimer's stuff is flunked, even though they approved that drug, which I think was a mega mistake. But, they may come out with something, which would be exciting. Yeah. But I think in the next 10, 20 years, I think it's very likely that there'll be therapies available. And then deep brain stimulation for things. I think the main thing that has to happen is it has to become available in remote parts of the world if it's ever really going to take off. So I guess focused ultrasound and other kinds of things. You can have you can have your pistol on your belt and bring it out.
So bringing the cost down, or making it more scalable, probably, right? Mm-hmm. Yeah. Okay.
Right.
Are there missed opportunities we should be taking at the moment? Things you think we should be doing, but we're not in the field, both science and clinical care?
Well, I think, and it's not clear at all. We're not collecting everybody's blood samples for DNA.
But
and we should be. Okay. Yeah. And that at the very least. And people should also be offering themselves up for trials pre-diagnosis. My mother had Alzheimer's. Yeah. Can you check me into a study sooner rather than later? That kind of thing, I think, is critical.
That's a good idea. Yeah. Okay. All right. So are there any topics before we wrap up that we did not cover today, but you would have loved to talk about? I know it was a long discussion already, but anything you wanted to talk about?
This is fun.
All right, Professor Young. So thank you so much. This was really great. All the best. I envy you in the nature with loons and your dog, and hope you have a pleasant day.
Thank you so much. Really enjoyed it.